Hi, everybody. Welcome back to Leah's Lifestyle. And we are on another day of practicing coding. So let's not waste a second. Get into it. Where were we the other day? Let me just pull some of these out. I had some other things open for some other reasons, and I just want to save them for later. Okay. We were in the middle of linear fractions.
Now that we've worked through the core skills in this unit,
I'm pretty
let's look
sure
through
I
some extra
listened
problems, and I'm going to work through extra problems using the CoLab notebook, so you can see how.
to at least like 17 minutes worth of this. I'm only guessing that because I'm got some of this stuff written down. I was pretty sure we had started at least, so we will bring these up. Oh, there we are. Display capture. Ta-da! Da-da-da-da! Alright, let me get my phone so I can see chat. How do you feel like? Twitch. There we go. I can see chat. Let's get down to business. Hold on a second. Yeah, that's perfect. Works for me. Shoot up. Alright, let's see.
How you can apply these resources that you're building and use these to solve problems that might come up in the textbook or in day-to-day life. So we're going to go through some more extra problems here. So we're looking at how we can apply some of the things that we've been doing to real-life situations and use this information to predict things, to figure out some trends, and real life or things that show up in a textbook that hopefully are realistic enough. So let's take a look at some examples here.
Okay.
And we'll work through these. So if we look at 25, a town's population increased at a constant rate. In 2010, the population was 55,000. By 2012, the population had increased to 76,000. If this trend continues, predict the population in 2016. So we want to notice.
Yeah, we did do this
that
already.
These are two XY coordinates, time and population. And time, if you have it, it's going to be on the x-axis almost all the time. So if we look at this, so 2010, 55,000, 2016, 76,000. Or 2012, 76,000.
Let's see how far
time and population. And I like seeing the grid, especially for this situation, so I'm going to put that in as true. So we have these details that you could have your setup and have these all commented out. All you need to do is uncomment them as needed. And then there we go. We're going to plot this linear.
This is getting closer.
Doesn't cut it. So we have to go to X minimum and maximum. That's fine. Y minimum. That's fine. But Y maximum, it can't be 150. Maybe I'll call it like 900. So you see, then
that's getting
according to this
closer.
trend, times 0, and that would be, at 17 vision, negative 0.3x plus 11.5.
Did we find our spot?
And we see this downward trend over time. And here's another one where if I wanted to change these tick marks, maybe
that's the last thing we were talking about
this
for sure.
To the X ticks.
Yeah, here.
Is 2 enough? Yeah. You can see this downward trend, down 0.3. So it should go, over 10. It just
okay. Yeah. So we were about 23 minutes into it yesterday. So bring your video about there.
No profit, because that's the trend we're saying. There you go. So whatever this company is, this is their profit since 1980, and then there we go. 38 years later, then they would have no more profit. So who knows what company this is, but our fictional company is
A fictional
something would have to
company.
change. But that's where the prediction lines, the the simplest prediction is, okay, these would go in a straight line. Whatever trend would continue in a straight line unless something changed. But we know that
Right.
in normal business, normal day-to-day life, things do change, and that's why our lines aren't always perfectly straight. But this gives us often enough of a prediction. Oh, and you see then time and then cases, then we change that to profit. Okay, just to make it efficient here, time and profit. So there we go, another situation, and we can see where it would start. And
Yeah, time and profit.
then
That's where we're at. Yeah, so
profit
about
declining.
24 minutes.
And that's enough years that 11.5 million was a lot more money in 1980, and then profit declining, and yeah. So this company is definitely, whatever they were doing, they were in sad shape. All right, and we have the y-intercept and all that. Okay, so we see another very similar. We'll do one more here. So consider this scenario: 2004 school population was 1,700. By 2012, the population had grown to 2,500. So, all right, and again, assume the population is growing linearly. All right. Now, how much did the population grow? So this, A, is really just the subtraction. So 2,500 minus 1,700 is 800. So it grew that much. And then the average per year, you see, anything per year, the rate, that's the slope. And
That's the slope.
we can divide that, but we're also going to then just plug these numbers in, and you'll see that we can see the slope. So 2004, maybe we'll call that time 0. 2004, 1,700, 2012, 2,500. And I might even leave the hundreds because we want it to be, more exact. We know that the population would be continuous; it wouldn't just jump hundreds. So, 1,700, and then minimum, and then we have 2,500. So then,
Whoops.
after this, if I wanted to graph this, then my y maximum on the I put it wrong. So there you go, times 0, 1,700, and so in 2012, so times 0,
Wait.
and then in 2012, so that's 8 years later, it was
I
2,500.
saved these.
So 8 years later, then it was 2,500.
Go back. Hold on. Hold on. My bad. I want to save these because I want to remember what they looked like. So just give me a second.
1,700, and then minimum, y maximum, So let's just, years later, then it was 2,500.
Wait.
Um, 1,700, and then minimum, and then we have 2,500. So then, after this, if I wanted to graph this,
Yeah.
then
Go up to the top.
my y maximum on the I put it wrong. So there you go, times 0,
5, 10, 25, 4. Roll that. Goody. That's what we wanted. Second, he's gonna start changing everything. I want all of this here.
$1,700, and so in 2012, so times 0, and then in 2012, so that's 8 years later, it was 2,500. So 8 years later, then it was 2,500.
Oh.
There we go. Okay, so we'll have that, and eximid.
And then he changed this to. Okay, now I'm back on topic.
And then the x maximum. So let's just make it a nice even 10.
Oh.
And we could always change it if we need to. Y maximum.
You just
2,500,
changed
we're going
it.
a little bit further.
Oh, he was typing it in the wrong spot.
Let's make it
That's
3,000
why.
and see if that's going to be enough.
I understand. He was messing up.
There we go. And do I want the ticks for right now? See, if you comment them out, the graph will, as we saw, it will still give you the tick marks. It's just that the default whatever Python wanted to calculate, and where you can force them into however often you want. There we go. And for school population. Go. All right. So we see it's growing by about 100 a year.
Okay.
And maybe that's, depending on what you wanted to estimate, these tick marks might be fine, the grid might be fine. And, if you wanted to, you could always add more or change it. I think that works out. So, growing by 100 every year, and we can use that to predict. So, the average growth per year was 100. There we go. 100x, so the slope is 100. And there's the equation for the population for T years after 2004. So we see.
I feel like I need to memorize these, but I'm not sure how.
Population model, but there's some other practice problems that we see in other tech. All these are coming from that textbook, the second textbook, Algebra and Trigonometry, because there's a lot of good business applications in it.
So I should get that textbook.
Here's the idea that
Algebra and
just the notation,
Trigonometry.
G equals F of P, the amount of garbage G produced by a city with a population P. So we can go G equals F of P, and that's how we would read that. So it's a function of population.
Yeah.
And what that tells us is population is the independent variable.
Function of population.
And then garbage is the dependent. And population very often is an independent variable that causes a lot of other trends. So we look at that, and we see the same type of thing. Town of Tola has a population of 40,000 and produces 13 tons of garbage each week. Express this information as a function. So.
And that's when you use the
now,
F in the parentheses, so the
this,
function of said thing.
One of the things that we would guess is
4,000 and
if it's a
produces
function
13
of
tons
population,
of garbage, so the
then
function is
no
creating
people
garbage.
would mean no garbage. So in our y equals mx plus b scenario,
Right.
b would be 0. And notice because we only get exactly 1 point here, 40,000, 13 tons. So if we wanted to set this up, we want to look, we know that we have the Python scripts to solve this, but if we want to set this up, we want to take a look at how we're going to set this up. 40,000 is going to be the population, and who knows, maybe I might just call it in thousands, and then 13 tons, same thing, I'll just call it 13. And then we say, well, that's 1 point, where do I get the second one? But we have to look at the situation, would I think that it would start at 0, 0? And if that's the case, then we could go back and say, so here's 0, 0. And then, remember, our x values are going to be population, so we'll call that 40.
But now this is a different thing, right?
And then that's going to be 13 because it's in tons.
Okay, so instead of putting 40,000, he put 40.
0, fine. But x maximum, 40 is probably not even enough because we start with that, and we can expect that it increases.
Right.
So then,
how much are you expecting it to increase?
Let's say the x maximum would be, I don't know, let's make it 100 and we'll see. Y minimum 0. Now, 13.
Probably.
Maybe make it like 50. We'll see if that's enough for y maximum.
Okay.
So there we go, and we can just write this in thousands, and we can make this in tons. So thousands of people, tons of garbage.
Tons. Thousands of people, tons of garbage.
This trend here.
Got it.
40,000 generates 13 tons of garbage. And we can see this trend here. So there's the rate here, 0.325 x. So remember that x value is in thousands. So every 1,000 people, according to this fictional scenario, makes 0.325 tons. So
this fictional.
That would be about tons 2,000 pounds. So that times 2,000 would be about 650. But then if that's thousands of people, so that's each person making less than a pound of garbage.
Less than a pound
Maybe.
of garbage.
So again,
Damn.
this is not the latest research. This is
This is not the latest research.
And then what's the meaning of this? And we read this as f of 5 equals 2. So notice that the function, like our functions in Python, that 5 is the input, and any input or independent variable, that's x, or, even though we call it p and g here. So that input 5 and then output 2. So f of 5 is 2. So we would expect then that that means that when we're talking about 5,000 people, then 5,000 people would produce 2 tons of garbage. So that's the meaning of that. 5 is the input, 2 is the output. So in our XY scenario here, that's what that would mean. 5,000 people would produce 2 tons of garbage. All right, and so let's go over here to 89, and another one. You see, don't get caught up in the alphabet soup of this as people use different notation. Notice the trend of, I would read this as g of a, so it's a function of this input a. So the number of cubic yards of dirt, d, is need to cover a garden with a square feet. So d for dirt is g of a.
I need to learn more shit.
And the common notation you'll see in just general math is f for function, and then often we just go through the alphabet f, g, h for other functions we want to talk about. In Python and pretty much across computer science, your function can and should have a much better name. So that's something that computer science has an advantage of. But nonetheless, you'll see this all the time. G of a. So again, we notice the trend. A is the input, that's the area, and then given that area, then how much dirt would it be? So we have 5,000 square feet area requires 50 cubic yards of dirt. So that 5,000 requires 50. Now, we're not even going to do any calculations to this, but I just want to show you that that would be G of 5,000 equals 50. So that's just how we would write that.
Okay.
Given that input, area that we would know first, then therefore how much dirt we need. And that would just be how we would write that. We don't need to do any math with that right now. And the same thing, G of 100 equals 1. So 100 cubic yards, or 100 square feet of garden requires 1 cubic yard of dirt. All right, and question 90, we'll see just another situation, f of t, so there you go, some function. The number of ducks in the lake after t years, after 1990. So f of 5 is 30. So we know 5 is the time, years after 1990. So in 1995, there were 30 ducks in the lake. And then f of 10, so in 2000, there were 40 ducks in the lake. And given these, you see we can x, y, we can find the overall equation, plot the points, graph it, make some other predictions. But that's the notation here, and this is what that means. All right, now, 91, the interesting thing is, for just answering these questions, this won't matter, but this is not going to be linear. But we can still answer these questions because each of these is still going to be the same. Now notice h of t, and now in this case h for height, but again, another way of expressing this. So as x, y values, x is 1, y would be 200. The h of 1 is 200, so that x value is t for time in seconds. So after 1 second, it's 200 feet up. After 2 seconds, it's 350 feet up. And again, this is not linear, so the same things that we've been doing actually won't work for this, but we can still get the meaning of each statement here. And 92, the one-to-one is, this is still a function, but that each x value and y value pair up, neither of them show up again. But this is a parabola because we see x squared, and we'll talk about parabolas later. But the one-to-one, there's actually positive x values and negative x values that might still have the same y value. So that's why it's just not one-to-one, but it's still a function.
Yeah,
I don't want to talk too much about that when we get to these types of functions later, but I just want to mention that in case you're looking at that and saying, well, what does this mean? So in number 60, now this is also not linear, and you see the height of a projectile is more like something like this. After t seconds, here's the function. H of t equals negative 16 t squared plus 96t. So that's showing that it isn't linear. In fact, it's a parabola because it goes up, turns around, comes back down. Okay, so the domain, anytime we talk about the domain, that's the x values. So the domain is all the x values that are possible here. And then the range, this doesn't ask it, but the range is all the y values. And this actually has a limited range. So because this is a parabola that goes up and then comes back down, there's a maximum y value. So after that y value, there's no, like, y values beyond that are not a part of the range because it'll just never get to those numbers. Then the domain, mathematically the domain is all real numbers. But realistically, in the context of the problem, times 0 would be the first part of the domain. So you see, mathematically, these other numbers exist and they don't break this problem. But realistically, if I'm launching something, it starts at times 0. And yes, I know that we can talk about t minus whatever and talk about negative values because we're awaiting the launch. And this is second, so if it's like t minus 10, then it's, the t value is negative 10, and that's 10 seconds until the launch. But realistically, we want this to be times 0. And then the other one would be, it does go up and comes back down. So there's a time where it hits the ground again, and beyond that, it's not really within the scope of this problem. So let's take a look at how we can solve this. Just because, even though it's beyond what this is asking, I want to find out what that t value is. When does it come back down to the ground? All right, so negative 16t plus 96t. We can go into this, where we're going to import our symbols. And instead of t, we're going to make it x, just because I already have x as a symbol. But you could always change it and make it t. That's fine. So negative 16, and again, we're going to use x squared minus 96 x. And that's always this is the equation set equal to 0, and that's what I want. What x value makes this 0? Now, negative 6.
He always just like has all this stuff already. There's not even anything he's had in here before. Okay, I gotta type all this shit real quick. I guess it's good for me. Import. And this is Simpy. Alright. From Simpy, import symbols. From Simpy.solvers, import solve. Okay, and then he says that the symbols x will look like this. Equation here. Oh, hold on. And the equation he just went over, which is the EQ equals the negative 16 times x times 2. Oh, it's like the upper whatever. Yeah, I forget about that. That's how you show. What is it? A higher whatever. 96 times x. Solution equals solve equation x. Whoa. Ahead. Print x equals solution 0. Okay, go on.
Would not be plus 96t. Oh, is that the minus?
Wait. Haha. Let's try that again. Okay. What was he saying?
Alright.
Oh, he plussed it here. Changed this to a plus, not a minus.
So, it only gives us 0. What if I have was doing this with things that only had one solution, so storing this as a finite set, and I just printed the first one. But this does have two solutions.
Oh.
You see? And, I mean, I could get really fancy here and then actually just make another print statement. But see, this is my finite set. It's not 0, 6 as a coordinate. It's x equals 0 or x equals 6. And I could then put this 0, and I could have another print statement.
And then
there we go, to show the first one. But this is just a matter of, how you want the output to look.
oh, that is so smart. So you can see both.
And we have these, we also have, which we looked at before, you could, loop through this to get solutions, to get multiple solutions. But there we go. Yes, x equals 0, it's on the ground, and then x equals 6. So that's another way that we could, graph this.
What if you had multiple solutions, though?
We see that back on the ground at 6. Now,
how would you make it repeat
we'll talk about quadratics later.
over and over again?
So,
that's what I want to know.
Yes, we will not worry about graphing this because we'll get into this with quadratics. But this gives us the solution that at 6 seconds later, it's back on the ground. So some projectile launched, it went up and turned. And I'll tell you this, that halfway through, these parabolas are symmetrical, so halfway through, it's at its maximum point. So we could even print here, what is that maximum point, and we can do that math. Negative 16. So halfway through that, so that would be 3, would be x. And you see, that's really the idea of it. You set up a situation where I have x, and I can plug in my value. So 0, 6 is back on the ground, so 3 seconds later, it goes 144 feet up in the air. So realistically then, the domain for this function that's practical, not just like, mathematically it exists, but related to this situation, the only x values that mean anything for this are anywhere between 0 and 6, including 0 and 6. Because everything else doesn't really mean anything for this situation. After this, then if it keeps going down, it doesn't go back down to the ground. And the y values here are between 0 and 144. So that's my domain between 0 and 6, including both. And the range between 0 and 144. So, these are some things we can look at, solve when equals 0, and plug in some various numbers.
I'm not tired, you're tired.
So, when we look at 61, just again reading as these, we might not even need to do any code for this. We have this situation, the cost of making x items is 10x plus 500. And the fixed cost is determined when 0 items are produced. So find the fixed cost. And remember, 0, so then if x is 0, that 10x drops out, and then we're left with 500. That's why it's B for begin. When, before we produce anything, the fixed costs are 500. Now maybe this is some sort of business, and 500 is like rent and utilities and everything, that even if they're there, they didn't make anything, they still have to pay all that. And then they pay $10 for whatever, whatever they make. So then the cost of making 25 items would be 10 times 25. We just plug that in, 250 plus 500 is 750. All right, and supposing the maximum cost allowed is 1500, what is the domain in the range? So, if we have to set this equal to 1500, now, if we take a look at this, and I'll just again write this here. So if we have 1500 equals 10x plus 500, and notice this isn't Python syntax because I'm not worried about doing anything with this yet. But then, what do I want to do? I want to put this equal to 0, so if I subtract 1500 from both sides, then I get 0 equals 10x minus 1000. Because if I subtract 1500 from both sides. And so that's set equal to 0, 10x minus 1000, then that's where I can plug this in here. So you see, you can work out the math then.
Okay. Which is why it's a text, that's what he's saying. So we type here. Isn't that the same? Isn't that the same? Anyhow. This. Wait. No. This he was about to change. Oops. So we're gonna put it here.
Before you get to the Python code. So 10, and then here I do need 10x minus 1,000. So if that's the case, now with this one, I know there's only one solution. So if I keep the other one, that's going to give me an error. So whatever it is, we know that you can only make 100 because maybe they only have that budget. Whatever they're making, they make 100 of them. The total expenses were 15. Total expenses were 1,500, and then we have to go out and sell whatever they are.
Oh, but we haven't found it yet.
Whatever else they're making.
Yeah.
All right. Okay, so we see these same types of things. I just want to look at the setup of this. That I did number 44 at the start of the trip. The odometer on a car read 21,395. At the end of the trip, 13.5 hours later, the odometer read 22,145. Here we go. Assuming the scale is miles. So average speed, we want to take notice that anything like a rate like that, that's slope, and we have two values, times 0 and then the miles, 21,395, and then times 13.5 and then the miles, and we can go through and plug that in. Whether I care about graphing this or not, it still will output the slope, which is the answer to this question, the average speed. And that's where average speed, it would be a linear function, whereas realistically we know, especially over 13.5 hours, the speed's going up and down, sometimes stopped, sometimes faster, sometimes slower, but we get that average speed. We know that whatever that answer is, we're not getting that exact speed the entire time. All right, and 45. The driver stopped at the gas station to fill his tank, and he looked at his watch, the timer exactly 3:40. This time he started pumping gas in the tank. Exactly 3:44, the tank was full. Now, if I was filling gas for 4 minutes, especially with these prices these days, I would be expecting it to be a lot more money. He noticed he had pumped 10.7 gallons. So, surprisingly, not that many gallons. But what is the average rate of flow of the gasoline? So, again, time is going to be x. So, if we want to call it minutes, we can call it 4 minutes, and then 10.7 gallons. So we could calculate to gallons per minute. Or, and again, same thing, plug it in. Actually this one, because we already did that subtraction, is just 10.7 divided by 4. So some of these, you have these scripts and everything available, but some of these you might be able to solve even before you look at those.
Yeah.
Or you could break down into seconds, how many seconds.
I feel like he's more explaining like how to get past these, which is fine. I'm not really sure why.
Gallons per minute is probably fine. So we see all these situations. We want to see, recognize how we can set these up. And the things that you're building that you already have to be able to solve an equation, even if, the equation is something else and you can just do one step of algebra, because that's it, you want to get it equal to 0. So keeping in mind from earlier, that one step of algebra, so that you have to equal to 0 and solve.
Become a supporter. I am a supporter. What are you talking about? I'm acquiring skills very quickly. I've never tried to code before, and I am learning how lots of stuff right now, okay? I actually have an app on my phone. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There's so many more. That's okay. Every day, just a little bit. That's the point. I started it, and I've been wanting to finish it, so. Okay, let's open up this collab book. See what is in here. Okay. What does the modulus operator do in Python? I'll guess that, but let's go in for it. Let's see what's up.
So when we talk about factoring in algebra, then we're going to talk about dividing out
Mm-hmm.
something. So any factor is something that we're multiplying.
Right.
And therefore, I'm looking for things like when I see a number, what am I multiplying? So when I see a number like 6, then I can say, oh, what are the factors? Oh, that's 2 times 3.
Factors.
And
too.
here I'll
Okay.
put the dot for multiplying to separate the factors. So, when I look at the number, like 15, then what are the factors? Oh, that's 5 times 3. And it's useful to be able to think about numbers and what are the factors, because that helps us reduce fractions and simplify other terms. So
Right.
for example, if I had, since I'll use these two numbers here, supposing I had a fraction that was 6 out of 15. And I said, oh, well, I want to reduce that fraction to lowest terms. There's a better way to write this. So then
Right.
if I remember that they both are divisible by 3, that 3 is a factor of both of these, then I can say 6 divided by 3 is 2, and 15 divided by 3 is 5. And so this is that reduced fraction. And I got this by factoring. I recognize the common factors, and I divided out those common factors.
Okay.
So just like other parts of algebra, if I do the same thing to the left side of the equal sign and the right, then it's still
You're
equal.
finding it.
Here, with a fraction, if I do the same thing to the top as I do to the bottom. But that has to do with just multiplying and dividing. Adding and
Right.
subtracting doesn't work. So if I have these, I can reduce, reduce my factors. I can even keep going. Supposing I had something like 6 out of 24.
Okay.
And supposing I didn't recognize that 6 was a factor of 24, but I at least saw that they were both even.
So
I
you knew
could
2.
then divide by 2.
Yeah.
6 divided by 2 is 3.
Right.
24 divided by 2 is 12.
Got it. And you just keep
I could
doing
start
that.
reducing, again, recognizing that common factor.
3,
Or
so there's a
then I could
1.
take it further. Oh, 3 and 12, both
Yeah.
divisible by 3. And then I could say 3 divided by 3 is 1, 12 divided by 3 is 4.
Yeah.
So
forth.
again, I factor things out and therefore reduce the fraction.
Got it.
Now, a lot of times, we see things and we see fractions and we can't, especially bigger numbers, we don't right away think about the common factors, and we can always do long division. In a couple minutes, I'll show you how to do this with code to set up a loop to find the common factors. That way, even if you don't see them or if it's a lot and, how do I go through all these possible factors, I'll show you how to write the code to develop a loop to do that, find those common factors. But this is one of the big uses of common factors. Another use, and this is more related to other algebra topics. We might not need this as much as far as writing code, but if I have something like, 4x plus 16, something like that, and I say, oh, these two, the 4 and the 16, have a common factor, which is 4, and I can divide that out, and we can divide it out like this way. So this is another use of the term factoring, because I see these common factors and I divide it out. 4x divided by 4 is 1x, so I'll just put x, and then 16 divided by 4 is 4.
Yeah.
So, and again, this has more to do with other algebra applications, but I want to show you this because this is also factoring out. Then, if I have this, I see the common factor, and I can divide it out, and it looks like this. Or I can distribute the 4 times x is 4x, 4 times 4 is 16, and go back to that.
Right.
So that's another use of the common
I
factor.
remember that. I remember doing that.
One of the
in
other
high
things
school.
we're going to do is talk about factoring out square roots. And
Okay.
that also, I'm going to show you how to do this, but then we're
Factoring
going
out
to look at the
square
code,
roots.
how to find common square factors, and then factor them out. But let's take a look at this. If I have a square root,
Yeah.
and sometimes we have square roots that don't work out evenly. They're not perfect squares, but I can factor them. And sometimes that helps because those factors cancel out with other things later. So if I have, let's say, the square root of 24. Now, square root of 25 is 5. That's great. Square root of 24, almost 5. It'll be some long decimal because it's an irrational number. But if I can factor that out, recognizing these common factors, and now in this case, I don't want just any factor. I want a square factor. So if I remember that 24 is 6 times 4, that helps because 4 is a perfect square. And then I can say, so I want to identify these factors, but I'm interested in the ones that are square factors, and 4 is square, so the square root of 4 is 2. And then since I took the square root of 4, I still have that 6 underneath the radical. So even if I can't square root the whole number, I can square root part of it and factor that out. So sometimes then, even if I can't factor out something like the square root of 24, I can get it down to something like this, and that's the simplified square root, this factored square root, and sometimes that's really useful.
Okay.
Now, again, bigger numbers,
Sometimes
things
it's really useful,
think about,
he
oh, this is a
says.
perfect square. We'll talk about how to write the code to find these perfect squares and divide them out, and even use the SymPy library to display it in a nice way. So that's really the essence of what we want to do with factoring. Recognizing factors of numbers, and this is where even if you're going to write code, the more you remember your multiplication tables, the better things will be. It just makes things, come together a little bit easier. But we're looking at numbers, thinking about what factors made that number, and then we're looking at common factors that we could possibly divide out. And so let's take a look at that. We'll take a look at the code. So here we're going to do the same thing we were doing with working it out by
Okay,
hand.
that's
Finding
here.
the common factors, dividing them out, and it's going to work a lot better with writing code because it'll go through and easily find all the factors for you. And to do that, we're going to use the modulus operator. So modulus, that is the percent symbol. So on the keyboard, it's the shift on the 5 key. So what that does is that finds the remainder. So I already ran this. So if you print 5 modulus 3, it's like 5 divided by 3. But the whole number answer doesn't matter. We just want the remainder. 5 divided by 3. 3 goes in there once with a remainder of 2, and that's what it'll print out, the 2. And if we want, we'll just comment this one out and uncomment this just to show you another one. So 31 modulus 10. So 31 divided by 10 is 3, but that part doesn't matter. It's a remainder of 1, so when we run it, it'll output 1. Now that's going to be important for finding factors, because a remainder means that it's not the number's not a factor. But if the remainder is 0, then it's a factor, and that's what we're going to do, use the modulus to find factors. So I just picked this number 12, and we're going to put this up in a loop. So in our loop, so I made this variable just called test factor. So we have for test factor in range 1 to the number plus 1. Because I'm dividing, so I have to make sure I start at 1. If I start at 0, it'll give me an error. And I want to include that number itself, so I have to do plus 1. Otherwise, it won't do that last number. So for test factor in range, and then we go to this line here. If number modulus test factor is 0, then it must be a factor. So then I'm just going to print out the test factor. So that's what this is going to do. Given my number 12 here, it's going to run through that and try each number and see if it's a factor and print it out if it is. So then when I run it, see it prints, there we go, 1, 2, 3, 4, 6, and 12. All of those are factors of 12.
Of 12, okay.
So how can I reduce fractions to lowest terms? So let's take a look at this, and I'm defining more variables here. My numerator, let's call it 12. Denominator, 24. Now we know that this is going to reduce to 1/2. And I'm going to define a variable called factor, which is 1. That will be a factor, and who knows, for some things that might be the greatest common factor. So now once I have my numerator, to find the greatest common factor, all right, so for test factor in range, 1, denominator plus 1, because that's really, I want to go up through everything in the denominator. Beyond that, the numerator, it's not going to really work out. So now, if the numerator modulus, so we'll do this line here, if the numerator modulus test factor is 0 and denominator modulus test factor is 0. So for each of those, if it's a factor of numerator and denominator, now that's going to be my variable factor. And then once I have that, now I'm going to divide that out. So I'm going to do numerator divided by factor, and I want to cast it as an integer because that's going to look nicer when we do, the sense of this is that they should be integers if they're factors. So this is going to look nicer when we display it. So once I find my factor, and it could stay at 1, or it's going to get the largest factor I can find. Once I find that numerator divided by factor, cast it as an integer, and I'll just call it n. Denominator divided by that factor, cast it as an integer, I'll call it d. And then we're going to print out the original numerator divided by denominator, and then the reduced fraction n divided by d. So let's run this, and we see that the original was 12 over 24, and the reduced is 1/2. So there we go. We can reduce any fraction, and you can even copy this code and use it within something else you have, or you can put this as its own function and deal with it that way. We'll talk about creating functions out of a lot of this code later on in the course. So
yeah, something I need to learn is how to create functions.
About adding it.
That's a big thing.
So we had the decimal to fraction code, and
I can't wait to learn
we
functions.
had an input rather than just have the number here. I have this input. I asked the user to enter a decimal number to convert, and remember then that input gets stored as digits, but it comes in as a string. And we've done this before, converted to a fraction. So I go here, the length of that input, how many digits, minus 1, well, convert it to an integer because, and minus 1 because that will come in as a string, that'll include the decimal place. So there we go, then that becomes my exponent, and then I'll still also cast that as a float number, which is n, and then as a fraction, my numerator is going to be my numerator here will be n times 10 to that exponent. So what that's doing is taking that value and moving the decimal place. So there we go. So n has all those digits, including the decimal place. Then this line for the numerator moves the decimal place, and then the denominator is 10 to that exponent. So now I have an integer for the numerator. This will end up being an integer for the denominator. And now what we're going to do is, just like we were doing earlier, I want to reduce that fraction. So same thing, factor equals 1. Everything else I already had. That same loop, finding the greatest factor, dividing it out, and there we go, inputting the decimal, which is the original number that the person entered, and then print the fraction. So when we run it, enter a decimal number to convert. So let's convert something like 0.125. There we go.
Do you see that he changed?
It took it and it reduced it to 1/8, which 0.125 is 1/8. And we can run it again just to see that if I have 0.02,
want to see.
There we go. Decimal, and then that's 1/50th as a fraction.
And you can use
So we can apply
change
that
it.
code into other things that we've been doing. All right, now we're going to take it to the next level, factoring out square roots. So this is all good to reduce the fractions, but remember when we square root something, now in this one, if I just print math.square root, there we go. Square root of 25 here is 5. Great. But what if I have something like the square root of 24? Now that doesn't work out nicely, and by default, it'll just give me that decimal answer. But what if I
Right.
want to factor it? And this is how we want to factor it. I use square root of 12 as an example. Square root of 12, because underneath the radical, 12 is 4 times 3. And then 4 is a perfect square, so square root of 4 is 2, and that comes out.
Yeah.
And then I have 3 left over, nothing else I can do with that. So that's the factored square root. We want to find our square factors and divide them out, the square root of that. There we go.
Import math.
So here we have number to factor. You could make a user interface, but I just put it here, n equals 12. And max factor, I just made that 1. That's the one that will change. And here's, I put this as the key ingredient because this is how we get to, if I have my loop, where do I start, where do I stop? So the upper limit of math.floor of math.sqrt of n. So I'm going to take the square root of that. Then that's going to be some weird decimal number. Now I just did this math.floor and then I added 1. I probably could have done math.ceiling also, but I just did it this way. So take the square root and whatever, math.floor, so drop all the decimal places, not round it, just drop them all, and then add 1. So that's going to be the upper limit. And now we want to go here. So for maybe factor in range, again, starting at 1, 0 given error to upper limit. If n modulus maybe factor squared, so you say I'm running through those factors, and each of these is the square root factor. So if I square it, n divided by that factor squared, if that's 0, then now that maybe factor is now my max factor. So we go through, and we're going to cycle through all these, divide it out, does this work? And once I get some factor, that's what's going to be on the outside. So then I have the results, my original number, square rooted factor, square factor, and there's a reason why I'm printing all of these out here like this, because we're going to build upon this and make it look nice in the next step. But to show that square rooted factor, max factor squared, and then the integer that's left over. So for 12, since we had that example earlier, we see that n is 12, and the square rooted factor is 2, square factor is 4, and the integer is 3. Even though I called it integer, that was just text, it actually comes out as a float. So what we have it.
Okay, we're gonna have to pause here, unfortunately. I have someplace to be, and I'll be back as soon as I can to start up another stream, probably to finish this painting, do some cleaning, work with the plants because they need my love and attention real bad, and maybe some gaming. But anyways, I hope you guys enjoyed the coding, and we'll see you guys tomorrow. Don't forget to like, share, and subscribe. Comment. What do you enjoy so far about learning about coding? It's a lot to take in. Bye.